Okay, let's look at a few more points concerning power factor correction, and let's do a couple more examples to show how the technique works. So first of all, just a few things to keep in mind. First of all, a power factor correction capacitor should always be connected in parallel across an inductive load, not in series. So step one, you're going to find the power factor correction capacitor will simply be across the load, and both of them will be connected directly to the source, as we already saw previously. Second thing is when performing power factor correction, the average power does not change. So power factor correction does not change the average power that's dissipated by the load. The only thing power factor correction does is it cancels out the Q, the reactive power of the load. That's its purpose. So let's work an example just to show this again. And in this case, let's assume we have a source connected to some load. And in this case, I'm simply going to give the P and the Q for that load. So here's our load. P is equal to 1 kilowatt. Q is equal to 800 VARs. So in this case, you can look at this and see by inspection it's got to be an inductive load because the VARs are positive. So Q is positive. And so in this case, the complex power of this load will be equal to 1,000 plus J 800 volt amperes. So I can just write that complex power directly. So in this case, I've got a voltage, and I'm going to add this AC voltage source. Will be connected directly to the load, and across this I will have my CPFC, my power factor correction capacitor. So in this case, we want the power factor to be equal to 1. So in this case, the Q of that power factor correction capacitor must be equal to minus Q of the load. In other words, QPFC must be equal to minus 800 VARs. And in this case, if I'm looking at the total power of the load with the power factor correction plus the load, so if I look at the total complex power, then what I'm going to get is that S total, the complex power combined of the capacitor plus the load, will therefore be equal to 1,000 plus J 800 plus 0. The real power of a capacitor is 0 minus J 800. So the real power is not going to change. Adding the capacitor does nothing to the real power of the system. But what it will do is it will cause the reactive powers to cancel out. And therefore what we'll get is that it's simply equal to 1,000 volt amperes. Or in this case, since P is equal, this is equal to P plus JQ, then P is equal to 1 kilowatt, and Q total is simply equal to 0. And I should actually say that more accurately, P total is equal to 1 kilowatt. All right? So this is what we're trying to do. We're trying to cancel that Q with that capacitor. So we need to choose the capacitor such that we get cancellation of the reactive power of the load. That's really all we're doing. And once you know what that Q needs to be, it's very easy to work backwards and figure out what the value of the capacitor needs to be. Now let's go through and let's work an example where we're going to plug in some different numbers. And in this case, we're going to look at two cases. We're going to look at a case where we completely cancel the reactive power, but we'll also look at a case where we only partially cancel the reactive power. Let's look at that. Let's consider the following problem. We've got a load, and for this load, I'm going to assume that the average power, pardon me, the apparent power, excuse me, is 2 kVA, 2,000 volt amperes. And the power factor is equal to 0.8 lagging. So given this, what does this tell us about our load? Well, in this case, we know that our load is going to be equal to, S sub L is going to be equal to 2,000 times 0.8, since that's the power factor, plus J times 2,000 times the sine of the inverse of, the sine of the inverse cosine of 0.8. So all I'm doing here is I'm simply taking these values and plugging them into the equation. So in this case, I've got my apparent power. My cosine theta sub v minus theta sub I is already given. It's lagging. And then if I take the inverse cosine, I'll get a phase angle, which I can then calculate and plug into the sine. So this comes right out of that complex power formula. Okay? In this case, for my source, I'm going to assume that this is 120 at a phase angle of 0 degrees, volts RMS. And I'm going to connect a power factor correction capacitor in parallel with this load. Okay. So what do we have here? I have two questions. First, what value of CPFC gives us a power factor of 1? So just as we've already been seeing here, what value gives us a power factor correction of unity? But I also want to ask the second question. What value of power factor correction gives a power factor of 0.9 lagging? In other words, what if I want to improve the power factor? I want to increase it, but I don't need it to go all the way to unity. Can I actually calculate that? Well, let's go through and calculate both these. All right, so Over here, we've got our equation for complex power. If I multiply this out, this will be equal to 2,000 times 0.8 plus J times 2,000 times sine of 36.87 degrees, which will give us 1,600 plus J times 1,200 VA. And so just going through and plugging in the values, that's what we get for this load. So for a power factor equal to 1, if I want a unity power factor, then what I want is to cancel the 1,200 VARs of the load. So I must cancel that out with my power factor correction capacitor. Another way to think about it is this. Here's my total, my combined power factor correction capacitor plus the load. And in that case, what I get is that S total must be equal to my load, S sub L, plus SPFC, the complex power of the load, plus the complex power of the power factor correction capacitor, which must be equal to 1,600, plus J 1,200, plus 0, plus J QPFC. So I know that the real power of the capacitor is equal to 0. So just to go through and explicitly calculate this, what I want is this. If I group these together, this is equal to 1,600 plus J 1,200 plus QPFC. And this must be equal to 0. For a power factor equal to unity. And so therefore, QPFC is equal to minus 1,200 VARs. So exactly what we've been saying here. I just did this more explicitly going through the math. But what we're saying is we need to cancel the load, the VARs of the load, which means the capacitor must have minus 1,200 VARs in order to make that happen. And if that's the case, we can now go through. I'm going to define a current IPFC flowing through that capacitor. And so what we get is that, in this case, SPFC is equal to minus J 1,200 VA, which is equal to the voltage, this voltage here, the voltage across the capacitor, times IPFC complex conjugate. And the VPFC is, of course, just the 120 volts RMS, which is just equal to 120 volts RMS in rectangular form. And therefore, what I get is that this is equal to 120 times IPFC complex conjugate. So from here, IPFC complex conjugate must therefore be equal to minus 10 amps RMS, easily calculated from this equation, and therefore IPFC must be equal to J 10 amps RMS. And therefore from here we know that ZPFC. The impedance of that capacitor must therefore be equal to ZPFC divided by IPFC. Once again, just the definition of impedance. Once again, plug in the values. 120 divided by J10 gets us minus J12 ohms. And I know that this must also be equal to minus J over omega CPFC. Once again, definition of impedance. So what is omega? Again, if we're assuming North America, the frequency is 60 hertz, and therefore omega is equal to 2 pi f is equal to 120 pi radians per second. And therefore, I can plug omega in, and what I will get is that CPFC will be equal to 221 microfarads. So here's the value of the capacitor we need in order to get a power factor of unity. Now notice, just wanted to point something out here. I knew my power factor was 0.8 lagging. When I took the arc cosine of 0.8, because it was lagging, I knew that the phase angle had to be positive. If I take the arc cosine, I can get either positive or negative 36.87 degrees. But because I was told it was a lagging inductive load, I know it had to be a positive value. So there was a reason why I chose the positive instead of the negative value. If this had been leading instead of lagging, I would have been calculating sine of minus 36.87 degrees. So I just want to kind of point that out. The lagging versus leading is important because it tells you what the sine of that power factor angle has to be. Okay? So this is nothing more than something very similar to the example we did earlier. But now let's do something a bit different. The second part we were talking about. What value of CPFC gives a power factor of 0.9 lagging? In other words, what if we want to increase the power factor, but we don't need to set it to unity? We want to only partially correct the power factor. Let's go through and work that. Now to make this work, we have to keep in mind what I mentioned before. Earlier when I said that the real power never changes. Adding this capacitor does not change the real power of the system. P must remain the same. So, for PF equal to 0.9 lagging, keep in mind that the total complex power must be equal to P total plus J Q total, which by definition must be equal to the apparent power times the power factor plus J times the apparent power times the reactive factor. Once again, the basic definition of complex power. So that's going to be our total value of complex power for power factor equal 0.9, which means that we're going to have this equal to, from this, we see that P total is equal to S total, apparent power, times 0.9. All right? So I just simply plugged in our desired value of power factor, knowing that this is equal to this and this is equal to that. Q is equal to this, P is equal to that. Well, P total is the same as it was before. P total does not change. So what we have here is this is still equal to 1600 watts. That was the average power of the load. For the total system, it will still be the average power. And so then this is equal to 1600 is equal to, in this case, S total times 0.9, and therefore this gives us a value of S total is equal to 1778 volt amperes. So that's the apparent power of the system, assuming the power factor is equal to 0.9. And notice how I'm just going through and using the definition of complex power and the equations we previously developed. So in this case, all right, so in this case, let's go through and now let's take this number and let's plug it into the above equation. And so what we get then is that Q total must therefore be equal to 1778. In other words, this must be equal to that. So I plug in my apparent power times the sine of the inverse cosine of 0.9. So that's our desired power factor, and in this case, this gives us 775 VARs once we calculate this. Once again, when I take that inverse cosine, since it's a lagging power factor, we're going to choose the positive power factor angle. Okay? So, given this, let's now go ahead, and what this tells us is that Q total must be equal to Q load plus QPFC. The total reactive power in the system must be equal to the reactive power of the load and the reactive power of the capacitor, power factor correction capacitor. Well, in this case, Q load is equal to 1200. The reactive power of the load isn't changed, plus QPFC must be equal to 775. And therefore, QPFC will be equal to minus 425 VARs. So we're partially canceling the reactive power of the load. Not completely, just partially. And that's how much we need to cancel it. So in this case, what this tells us then is that the complex power must therefore be equal to minus J 425 VA for the complex power of our capacitor. And once again, this must be equal to 120 times IPFC complex conjugate. I can go through and calculate just as I did before, and what we get is that IPFC will therefore be equal to J 3.541 amps RMS. And from here, I can now go and calculate the capacitance. First of all, from here, I can now calculate the impedance. So ZPFC is equal to 120 over J 3.541, and that will be equal to minus J 33.9 ohms. And from here, this is equal to minus J over omega CPFC. I still have the same value of omega, 120 pi radians per second. And therefore, what I get is that CPFC will therefore be equal to 78.3 microfarads. So it's a kind of a messy calculation going through every step here, but you can see how everything makes sense. You're going through, you either completely cancel the power factor, or pardon me, cancel the reactive power to give you a power factor of unity, or you can partly cancel the reactive power to give yourself a power factor that is larger but not quite equal to unity. And you notice, of course, if I made the capacitor too big, I could actually push the total complex power such that I had negative VARs in the entire system, and I could actually have a overall power factor that would be leading instead of lagging. So obviously you want to be careful that when you do power factor correction, you correct just enough to cancel the reactive power of the load without going overboard, without generating excess negative VARs, because then your power factor starts going down again, except now you've got leading instead of lagging power factor. So interesting thing here, like I said, it's a little bit tricky to go through and work this out, but as you can see, if you just follow the basic math we've already learned in terms of how we define complex power, everything works out very nicely as you go through and do the calculations. So in a nutshell, what this has done is it's told us why we care about power factor, why we care about apparent power, why we care about reactive power. They matter because of the power company. The electric company wants as much as possible to eliminate reactive power. Reactive power forces them to make generators bigger than they need to be. And so the power company will make certain that they will, one way or the other, persuade their large-scale customers to do power factor correction. And they'll either charge them for it, or else they'll offer them the ability to do power factor correction, and they will supply that for their customers. Or the customers will do it for themselves. So that kind of wraps things up as far as power factor correction. Next time we'll spend just a couple more, look at a couple more minor points in terms of how we think about complex power, and that will wrap things up for Circuits 1.